Question 5 from paper 1 of the 2022 Higher Physics examination from the SQA. During an experiment, a student inside a lift stands on a Newton balance. That's a scale. And the mass of the student is 50 kilograms, and the lift accelerates upwards at 1.2 meters per second every second. And we have to find the reading on the Newton balance, and we're given our 5 choices there. Okay, let's take a look at the forces which are going to be acting on that scale. The scale is represented by that white bar there, that white rectangle. Well, we know that the person's weight, W, is acting down on the scales. And we also know that the scales themselves are going to be pushing back onto the person like that. And if the person is not accelerating, you can see that the weight of the person is going to be perfectly balanced by the reaction force due to the scales. Remember, the reaction force comes from the scales pushing up on the person, just the same way as if you stand on a bed and the bed sinks down till you get to a position where you're standing still in the bed. It's because of the springs pushing up on you, which is balancing your weight. So that's the situation we have, the weight pushing down in the scales and the reaction force of the scales pushing up like that. And everything's all balanced. But in this situation, we've got an unbalanced force taking place. And the unbalanced force is always equal to the mass times the acceleration. Now, if we take everything upwards as positive, we can write out the forces which is happening in this situation. So we have got the upward force of the reaction force, which is the scales pushing up onto the person, and we have to take away the weight of the person pushing down on the scales, and that's going to give us an unbalanced force. An unbalanced force is equal to MA. Now we know the reaction force R is going to be minus mg because weight is equal to mg, so that's the second line of our equation. Now we can rearrange things. We have R on this side and we take mg over to the other side, and we'll just have simply plus MA. And there is our equation which tells us the value of the size of the reaction force pushing up onto the person, and that's going to give you in fact the reading on the scales. So the reading on the scales is the person's weight plus whatever he's accelerating at multiplied by his mass. And you can see quite clearly from that, if the acceleration is 0, then the reaction force is equal to just simply mg, and that'll be the reading on the scale. But in this case we have an acceleration, so the reading on the scale R is going to equal to the weight of the person, which is 50, the mass times the gravitational force of attraction, 9.8, and we've got to add on to that 50 plus the acceleration of 1.2, and since it's accelerating upwards, it's got to be a positive 1.2 like that. So our equation is ready to be solved. The reaction force is going to equal to 50 times 9.8. That's going to give us 490 newtons. I'm going to have plus 50 times 1.2. That's going to give us 60 newtons. So altogether the reaction force, which is the reading on the scales, is going to be 490 plus 60, which is going to give us 550 newtons. So our answer to that is the reading of the scale will be 550 newtons. The scale will show a bigger weight than what the person's weight is when he's not accelerating. So the answer to that looks like it's going to be letter D. Question 6 from paper 1 of the 2022 Higher Physics examination of the SQA. Water falls at a rate of 1 times 10 to the power 6 kilograms per second over the Victoria Falls. The Victoria Falls are 120 metres high, and you have to find the total power delivered by the water in falling through 120 metres. And I've given you 5 responses. Okay, let's take a look at the picture of what's happening. There's what we have here. We have the Victoria Falls, and the water at the top is falling 120 metres down to the bottom. Now when that happens, it's going to have the water at the top is going to have a certain potential energy, and we know how to work out the potential energy. Potential energy EP is going to equal to simply the mass times g times the height from where it started from, if we take the reference level to be the bottom. So that water at the top of the falls will have a potential energy of mgh. So we can work out, if we imagine just 1 times 10 to the power 6 kilograms falling down there, we can work out the potential energy which is going to be transferred into kinetic energy at the bottom. We can work out the energy transfer. And we know that's going to happen in 1 second, therefore we can find the power, because power is energy transferred per second. So let's work out the potential energy of 1 times 10 to the power 6 kilograms of water at the top of the Victoria Falls. Well, all we have to do is work it out like this. We simply just do EP equals mgh. So the potential energy at the very top is going to equal to the mass of water we're looking at, which is going to be 1.0 times 10 to the power 6 multiplied by 9.8 and multiplied by the height in which the water is up from the bottom. So we work that out in our calculators. We find out that the potential energy comes out to be 1.176 times 10 to the power 9 joules. Okay. Now that potential energy is going to be transferred into kinetic energy, so your energy transfer is going to take place in 1 second. So the energy transfer is going to be taking place in 1 second. Transfer in 1 second, and that's going to be equal to 1.176 times 10 to the power 9 joules, and that's going to happen per second. But we know that joules per second is equal to a watt, so therefore we have 1.176 times 10 to the power 9 watts, and that's going to be the total power delivered by this water. Now, since we're using just two significant figures, we will write down the final answer as 1.2 times 10 to the power 9 watts, or 1.2 times 10 to the power 9 joules per second. It's all happening in 1 second. So the answer to that is going to be letter B. 1.2 times 10 to the power 9 watts. It's going to be B.